What if I told you that right now, at this very moment, time is moving at different speeds for different people? That your head is aging faster than your feet? That the faster you move, the heavier you become? And that space itself can bend and stretch like fabric? You might think I've lost my mind, but I haven't. I've simply learned to see what's actually there. My name is Albert Einstein, and I spent my life discovering something extraordinary. The universe doesn't work the way it appears to work. Reality itself is stranger, more beautiful, and more surprising than anyone imagined. And today I want to show you why. Let me take you back to when I was younger, working at a patent office in Switzerland. I had a simple job examining other people's inventions, but my mind was always wondering two bigger questions. One question in particular wouldn't leave me alone. Imagine you're on a train, moving very fast. You throw a ball forward to you inside the train. The ball moves at whatever speed you threw it. But to someone standing outside, watching the train pass by, the ball is moving at the speed you threw it plus the speed of the train. This makes perfect sense, doesn't it? Speeds add together. We all learned this. But then I thought about light. Light travels at an incredible speed, about 300,000 kilometers per second. So I asked myself, what if you're on that train, moving forward, and you shine a flashlight ahead of you? According to the old logic, someone standing still outside should see that light moving faster than normal, right? The speed of light plus the speed of the train. But here's what shocked me. That's not what happens. No matter how fast you're moving, no matter if you're standing still or flying through space at nearly the speed of light yourself, you will always measure light moving at exactly the same speed, always 300,000 kilometers per second, never faster, never slower. This discovery broke my brain. It didn't make sense, but nature didn't care what made sense to me. Nature simply showed me what was true, and when I accepted this truth, everything else began to fall into place, like dominoes. If light always moves at the same speed for everyone, then something else has to change. And what changes is time itself. Let me explain with a thought experiment. Imagine you have a special clock made of light. It's simple. A beam of light bounces up and down between two mirrors, and every bounce is one tick of the clock. Now imagine you're holding this clock, standing still. The light goes straight up, bounces off the top mirror, comes straight down, bounces off the bottom mirror. Tick, tick, tick. Now imagine I'm watching you from the side, but you're moving past me very fast on a train. From my perspective, what do I see? I see that beam of light traveling not straight up and down, but diagonally. It has to travel a longer path because while the light is moving up, the train is moving forward. The light has to go up and sideways to hit the mirror. But remember, light always moves at the same speed for both of us. So if the light is traveling a longer path from my perspective and it's moving at the same speed, then it must take more time to complete one tick of your clock. Your clock is running slower, not because there's something wrong with it, not because of friction or mechanics, but because time itself is moving more slowly for you than it is for me. This is time dilation. The faster you move through space, the slower you move through time. It's not an illusion, it's real. If you flew away in a spaceship at very high speed and came back, you would have aged less than me. Your watch would show less time passed. This has been tested. We've put atomic clocks on airplanes, flown them around the world, and when they landed, they showed slightly less time had passed than identical clocks that stayed on the ground, exactly as I predicted. And it gets stranger. Not only does time slow down when you move fast, but space itself contracts. If you're on that fast-moving train, the entire train actually becomes shorter in the direction it's moving, from my perspective outside. Not by much at normal speeds, but at speeds close to the speed of light, the effect becomes dramatic. A train that is 100 meters long when standing still might appear to be only 50 meters long when moving extremely fast. Now you might wonder, why don't we notice this in everyday life? Because we move so slowly compared to light. Light is breathtakingly fast. Even an airplane traveling at top speed is a snail compared to light. The effects are there, but they're tiny, invisible to us without precise instruments. But I realized something profound from all of this. We can't think of space and time as separate things anymore. They're woven together into a single fabric, space-time. You're not just moving through space, and you're not just moving through time. You're moving through space-time, and the faster you move through the space part, the slower you move through the time part. Together, your total motion through space-time stays constant. Think of it like this. Imagine you're walking north. That's your total speed. Now, if you turn slightly and walk northeast instead, you're still walking at the same total speed. But now some of that speed is going north and some is going east. The more speed you put into going east, the less you have for going north. Space and time work the same way. The more of your motion goes into moving through space, the less goes into moving through time. This understanding led me to another discovery, perhaps my most famous equation, E equals mc squared. What does this mean? E is energy, m is mass, and c is the speed of light. The equation tells us that mass and energy are the same thing, just in different forms. Matter is energy, just concentrated, locked up in a form we call mass. Why does the speed of light appear in this equation? Because the speed of light isn't just about light, it's the speed limit of the universe itself. It's the conversion factor between mass and energy, the speed at which all massless things travel, the cosmic speed limit that connects space and time. This equation tells us something incredible. Even a tiny amount of mass contains an enormous amount of energy because the speed of light is such a huge number and we're squaring it. A single kilogram of matter, if you could convert it all to energy, would release as much energy as burning millions of tons of coal. The sun is doing this right now. Deep in its core, it's converting mass into energy through nuclear fusion. Every second, the sun loses about 4 million tons of mass, and that mass becomes the light and heat that keeps us alive. The sun is literally made of light, frozen into matter, slowly releasing that light again. But I didn't stop there. Time dilation and space-time led me to an even deeper question. What is gravity? For centuries, people thought gravity was a force, an invisible pull between objects with mass, but I saw something different. I saw that gravity isn't a force at all. Gravity is the shape of space-time itself. Let me show you what I mean. Imagine space-time as a flat rubber sheet stretched tight. Now place a heavy ball on that sheet. The ball creates a dip, a curve in the fabric. If you roll a smaller ball near the heavy one, it will curve toward it, following the curved shape of the sheet. It's not being pulled by a force, it's simply following the natural shape of the surface. This is gravity. Massive objects like the Earth or the Sun curve space-time around them, and other objects simply follow that curvature. The Earth isn't pulling you down with a force. The Earth has curved space-time around it, and you're simply following that curve. You're taking the straightest possible path through curved space-time. When you're standing on Earth, you feel weight not because Earth is pulling you down, but because the ground is pushing you up, preventing you from following your natural path through curved space-time. If the ground suddenly disappeared, you wouldn't be pulled downward. You'd simply be free to follow your natural motion through the curved space-time created by Earth's mass. This explains something that had puzzled scientists for a long time. Why do all objects fall at the same speed, regardless of their mass? A feather and a hammer, if you drop them in a vacuum where there's no air resistance, hit the ground at exactly the same time. Why? Because they're not being pulled by different forces. They're both following the same curved spacetime. The curvature doesn't care how heavy you are. This theory, which I call general relativity, made predictions that seemed impossible. It predicted that light itself should bend when passing near a massive object, because light follows spacetime too. During a solar eclipse in 1919, scientists measured the positions of stars that appeared near the sun and found that their light had indeed bent exactly as I predicted. That was when the world started to listen. It also predicted something even stranger. Time runs slower near massive objects. If you stand at the bottom of a mountain, time moves slightly slower for you than for someone at the top, because you're deeper in Earth's gravitational field, deeper in the curved spacetime. Your head is literally aging faster than your feet, although by an amount so small you'd never notice it. But we've measured it with atomic clocks. It's real. So what does all of this mean? Why does it matter? It matters because it shows us that reality is not what it seems. The universe is far more elegant, far more interconnected, far more beautiful than we imagined. Space and time aren't fixed stages where events happen. They're dynamic, flexible, woven together, shaped by matter and energy. It matters because these aren't just abstract ideas. GPS satellites have to account for time dilation, both from their speed and from being farther from Earth's gravity, or they'd give you the wrong location. Nuclear power and nuclear weapons exist because of E=mc squared. We've detected gravitational waves, ripples in spacetime itself, caused by colliding black holes billions of light years away. But most of all, it matters because it shows us what's possible when we question what seems obvious. When I was young, everyone knew that time was absolute, that space was fixed, that gravity was a force. Everyone knew these things because they seemed so obvious from everyday experience. But I dared to ask, what if our everyday experience is misleading? What if reality only reveals its true nature when we look at extreme conditions, very high speeds, very strong gravity, very precise measurements? What if the universe is whispering secrets that we can only hear when we listen very carefully? And when I listened, I heard something magnificent. I'm often asked if these discoveries came from complex mathematics or brilliant insights. The truth is simpler. They came from curiosity, from asking questions like a child asks questions, without assuming I already knew the answers, from following the evidence wherever it led, even when it led somewhere strange. You can do this too. You don't need to be a genius. You need to be curious. You need to be willing to question what seems obvious. You need to look at the world and ask, why? How? What if? The universe is not hiding from us. It's here all around us, waiting to be understood. Every time you see light, remember, you're seeing something that always moves at the same speed, no matter what. Every time you feel gravity, remember, you're feeling the shape of space-time itself. Every time you look at the sun, remember, you're seeing matter transformed into energy, the ultimate magic trick of the universe. We live in a cosmos more wonderful than any story we could invent, and the best part? We're part of it. We're made of atoms forged in stars. We're arrangements of energy moving through space-time. We're the universe looking at itself, trying to understand itself. So keep asking questions, keep wondering, keep looking up at the stars and asking what's really out there, what's really happening, what's really true, because reality, when you finally see it clearly, is more beautiful than any illusion.